Bismillahirrahmanirrahim. Today is our lecture number 22. We have studied Lemma 3. Lemma 3 stated let the following diagram of R modules and their homomorphism. R module we have already studied what is homomorphism. About homomorphism we was already studied. Here we have f is a function from a to b, and alpha is a function from a to m, h is a function from m to n, beta is a function from b to n, g is a function from b to c, gamma is a function from c to p, k is a function from n to p. Be commutative with two exact rows. Then what will we prove? By taking help from here, we have proved that if by considering if alpha, gamma and h, if alpha, gamma and h are monomorphism, then so is beta. First part state that alpha, gamma and h. Where is h? This is h. Alpha, gamma and h is monomorphism, so what is beta? So we have proved that what is beta? Beta is monomorphism, isomorphism. What is beta? Second part state that alpha, gamma and g. Alpha, gamma and g is R epimorphism, then so is beta. So is beta. Alpha, gamma and g is epimorphism. So before starting off proof of this theorem, I have revised some definitions. Third part stated if alpha, gamma are isomorphism, alpha and gamma are isomorphism, H is monomorphism and G is epimorphism. H is monomorphism and G is there. This is G is epimorphism. Then beta is isomorphism. Beta is isomorphism. So this proof is talk around about beta. And first part state that alpha, gamma and h are monomorphism. So what is monomorphism? Monomorphism state that a function is said to be monomorphism if it is homomorphism plus 1 1. Epimorphism, what is epimorphism? Epimorphism is basically state that a function f from module m to n is said to be epimorphism if it is homomorphism plus onto. And isomorphism basically the combination of these both. From here we are taking homomorphism and 1 1. From here we are taking homomorphism and onto. So totally we have gained that homomorphism 1 1 and onto. So bijective homomorphism is called isomorphism. So by combining these both, we concluded this third part, I think little bit. So before starting off the condition first, I have revised the definition of homomorphism. What is homomorphism and what is 1 1? Or what is onto? So for monomorphism, basically 1 1 and homomorphism. So for homomorphism, we have proved there two conditions in the sense of modules theory. First condition, we have proved that f of m1 plus f m2 is equal to f of m1 plus f of m2. We are taking two elements from module. We are add these two elements and assign to a function. The result will be one element we are assigned to a function plus second element we are assigned to a function. The second condition will state that we are taking one element from a ring, R belong to R, and the second element will belong from a module, M belong to M. Then the multiplication of those two elements we assign to a function f. The result will be R f of M. So these two conditions we are proved that for homomorphism. For 1 1, we have proved that in a discrete structure, in a group theory, in a ring theory, in everywhere, when we are proved that the function is 1 1, so we are taking f of x is equal to f of y, then prove that x is equal to y, and will define is the converse of 1 1. And will define we have when we are proved that a function is defined, so we are taking x is equal to y, then prove that f of x is equal to f of y. So let's start the proof of this theorem. Here you have studied the structure of the theorem. Basically, f is a function from a to b and beta is a function from b to n. See the head of the arrow. One arrow goes from a to b, then from b to n, and here one arrow goes from A to M by using alpha, and then go from M to N by using H. So the composition of, in our last lectures we are also studied the composition of beta composition F is also equal to H composition alpha, and also gamma composition G is equal to A composition beta. So we have already studied in a previous 3-4 lectures. So I think here is no difficulty we have passed. Is a diagram is a commutative? It, by hypothesis it is mentioned that the diagram is commutative. From here it is mentioned that the diagram is commutative, so it is clear. And the two rows are exact. This is also given. The two rows are exact. This is also given. And this is also given by hypothesis if alpha, gamma, and H are monomorphism. This is also given. So by I also revised by a diagram H composition alpha equal to beta composition F H composition alpha. I also revised before in the start of the theorem, and also stated that gamma composition G is equal to K composition beta. So here write this, and image of F is equal to kernel of G. Let's see the function F and G. Image of F is here, and kernel of G is also belonging to here, because we are in a previous 3 lectures we are 2-3 times revised what is image of F and which is kernel of F. So after this, and image of H equal to kernel of K. Image of H equal to kernel of K. Image of H equal to kernel of K. So these elements belonging to M, and the image of F and equal to kernel of G, these elements belonging to B. So after this, to prove beta is 1, 1, we prove that beta is 1, 1. So for this, we have proved that by using very well-known result, a function is said to be 1, 1 if and only if kernel of function is equal to 0. In a group theory we are also studied, in a theory we are also studied, here we are also in module theory we are also studied. So here by taking the help from here, from this theorem we have proved that beta is 1, 1. So for this we have proved that kernel of beta is equal to 0. So from here we are taking B belong to kernel of beta. So then we are element, then beta taking, because this belongs to kernel of kernel. So those elements belonging to kernel which we are assigned to a function beta, the result will be identity in a codomain, in a range, sorry. Then beta of B is equal to 0 n, and beta belong to kernel of beta. After this we are taking both sides K, because K is here, from here K is also homomorphism. So we are taking both sides K. After this we are combine these two by using composition of functions. So K composition beta of B equal to kernel of 0 is equal to, when we are assigned identity to K, the result will be identity in a P, because K defined from N to P. K defined from N to P. So when we are taking identity from here and assigned to K, the result will be here like O. Okay, after this, K composition beta equal to gamma composition G. From here, K composition beta equal to gamma composition G. So by using this result, by using hypothesis, we have get this. After this, we are again reopen the composition of function. So gamma into G of B is equal to, after this, identity in a P is also equal to, when we are assigned identity taken from a C and assigned to a gamma. So the result will be also in a P. When we are taking identity from here, we assign to a gamma, the result will be here. So by using this function, we get this. After this, we are take out by using gamma is 1, 1. So we get G of B is equal to 0 in C. When we are taking element from a kernel, assigned to G, the result will be 0. So this element should belong to kernel of G. Okay. After this, kernel of G is equal to image of F. By hypothesis, it is given enough there. So this B, if of A is equal to B, basically image of alpha is belonging to image of alpha. This means that we are taking element from a function A from a set A and assign to a function f, the result will be b. If of A is equal to, then after this we are again taking both sides function beta. We are write again beta of b. After here we are combine composition of function beta composition f of alpha. After this we are used by hypothesis beta composition f equal to h composition alpha. By hypothesis we are again open the function of composition, so h of alpha of A, and we are taking beta from a function assigned to b. The result will be identity O, basically identity O and n. We are taking the element O is equal to h alpha of b. We are again taking, and we are taking those elements to h. The result will be m, because h defined from m to n. See the diagram, h defined from m to n. So we are taking O from here assigned to a function here. The result will be n in here. Basically this is O. Okay. After this is equal to alpha of A is equal to O, because h is 1 1. So far, and this is also equal to alpha from OA to m, because alpha is defined from A to m. So we are also right is equal to this. Sorry, I have pressed the wrong button. Okay, so alpha is 1 1, so A is equal to 0. And f of A, when we are assign A to f, the result will be like this, and is equal to 0 in beta. So b is equal to 0 by using f of A is equal to b. So kernel of beta is equal to 0. We are taking arbitrary element b from kernel of beta and prove that this element is equal to 0. So kernel of beta is equal to 0. So beta is basically 1 1. So by using 1 1, beta is R monomorphism. We have proved that. Next, what's the statement? Second part, what state? Second part basically state that if alpha, gamma, and g are epimorphism, then prove that beta is 1 1. Basically these are epimorphism, so we have proved that beta is also on 2. So for this we have proved that what? On 2. So we proved that beta is on 2. So for this, let n belong to n, because beta is defined from n to what? See the diagram. Beta is basically defined from beta b to n. Okay, so let n belong to n, then k of n belong to p by hypothesis is equal to k of n equal to p, and p belong to capital P by using function k. When we are taking element n belong to n assigned to a function k, so it should belong to capital P, and this is equal to small p belong to capital P. So by using this function we get this result. Okay, after this p equal to gamma of c, because see the function gamma is defined from c to p. C, gamma is defined from c to p. So we are taking element from here assigned to a function this, the result will be here. Okay, after this KNS we are write itself, and c is equal to g of b, because we are again write above this function like g from b to c. See here, g from b to c, we are taking element from here assigned to g function g, the result will be here. After this we are apply composition of function. This composition of function we have write gamma composition g, we have write k composition beta by hypothesis. So after this we are write basically kn minus k beta of b. We are open the composition of function, and it is equal to, we are common k and n minus beta 1, which is equal to 0 in p. Okay, after this these element we are assigned to a function k, the result will be 0. So this element should belong to kernel of k, and kernel of k is equal to image of f. So n beta of b is also belong to image of f, and basically image of f is when we are taking element from a function assigned to m, the result will be this. Assigned to h, the result will be this. So h of m is equal to n minus beta of this for m belong to m. After this we are write h and m. Basically alpha is a function from defined from a to m. So we are taking element from a belong to a, assigned to a function m, the result will be m in m. So by using this function we use this for some alpha is onto. So n beta of b, we are again combine composition of function and h composition alpha equal to beta composition f is equal to alpha. So we are write n is equal to beta of b plus beta of f of a. We are again open the composition of function, which is equal to beta into b plus f of a and beta plus f of a. So beta is our epimorphism. Follow from 1 and 2 whole. Third theorem state that third part what state that sorry third part state that if alpha gamma are isomorphism, h is r homomorphism and g is epimorphism, then beta is r isomorphism. So basically we see that this third part is basically the combination of upstairs two parts, because here we have proved that only one, here proved that only one, two. So here we have proved that these both 1 1 and undo. So follow from 1 and 2. We have already proved that 1 1 and undo. So the third is obvious. Okay. So this is the theorem of, this is the basically lemma 3. This is very well known result and very important result. If you have feel any complication in this theorem related to composition of function, modules, functions, sequences, commutativity and other things, if you have feel any complication in this theorem, so you should contact with me. Otherwise you have seen, go to lecture number 23. Inshallah we will meet in next lecture. Allah Hafiz.